Hi everyone, and welcome to the second of 4 videos going through some past exam questions on the topic of the halogens, the group 7 elements. Here we've got a long question here. It's a 5-mark question. What they're doing is something to do with displacement reactions. So they're doing some experiments to prove the trend in the reactivity of the halogens. We've been given various different solutions. Chlorine gas and chlorine water are not available, so we don't have any just chlorine. We've only got chlorine in a compound. Students carrying out the minimum number of experiments using these solutions to try and prove the trend in the reactivity. And they're doing it in the presence of cyclohexane, so we're going to have to be careful with what colours are going to be produced here. State the solutions that need to be added together in order to prove the trend in reactivity using the minimum number of experiments. So we want to do as little as we can here. Describe the colours seen and write an ionic equation. Okay, right, so if we don't have access to chlorine or chlorine water, we're going to have to use the barium chloride. Okay. So the solution needs to be added together. Okay, so the first thing we can do is add barium chloride to bromine water. Okay, we can do that reaction. Now, what's going to happen here is the bromine is not going to be able to displace the chlorine. So this will not result in a reaction. Showing that chlorine is more reactive than bromine, because the bromine is not going to be able to displace the chlorine. Okay, and it wants us to say what colour would we see. We'd still get the orange colour from the bromine water, because it would still be there, because nothing would have happened. Remember, bromine water is an orange colour just in water, and it's still an orange colour when we've got the cyclohexane. That doesn't change. Okay, and we can't write an ionic equation for that because there hasn't actually been a reaction. So that proves that chlorine is more reactive than bromine. Now we need to prove that bromine is more reactive than iodine. We don't need to do chlorine and iodine, right? If chlorine is more reactive than bromine, and bromine's more reactive than iodine, then we've put all three of them in the right order, haven't we? So what we can do here, we want to actually have a reaction, don't we? Because we need to write an ionic equation. So this needs to actually work. So we need to use bromine to displace iodine. So we can use the calcium iodide. So we can add calcium iodide to bromine water. This will result in a reaction. So bromine will displace the iodine. And because we're in cyclohexane, then we're going to get a purple colour. Okay, that's the point of the cyclohexane. The iodine is usually sort of a reddy brown colour in aqueous solution, but if you put it in the cyclohexane, then you get that purple colour, and that makes it much clearer to see the difference between that and the orange of the bromine water. And then this one, we do want to write an ionic equation, so we're going to have our iodide ions reacting with the bromine to end up with the iodine being displaced and the bromide ions in the compound. Okay, I think we're done here, right? So we might just add here, if bromine displaces iodine, this proves that bromine is more reactive than iodine. And so we could then say, therefore, the order of reactivity is chlorine, then bromine, and then iodine. Okay. So I think we've done everything. We've said, here's a reaction that shows that chlorine is more reactive than bromine, and we've said the colour. Here's a reaction that shows bromine is more reactive than iodine, and we've said the colour. We've done our ionic equation. That's it. We don't want to do any more because it said do the minimum number of reactions. That's actually all we need, just 2 reactions. So I think we're done there. If we have a look at these other questions. So here it says, chlorine reacts differently with dilute and concentrated solutions of sodium hydroxide. When it reacts with dilute sodium hydroxide, one of the products is sodium chlorate 1, This is a reaction that's used to make bleach. When chlorine is reacted with hot and concentrated sodium hydroxide, a different reaction takes place, and we get this NaClO3. In each reaction, chlorine has been oxidized and reduced. What term is used to describe a reaction in which it's oxidized and reduced? So this is our disproportionation reaction. Write equations for these two reactions. So this is the thing, you just need to know these reactions. Okay. So chlorine's reacting with dilute sodium hydroxide. So we've got chlorine, it reacts with sodium hydroxide. Okay. What we end up making is sodium chloride and this sodium chlorate 1, which is NaClO, and then the hydrogen ends up in water. Okay. And then in terms of balancing here, we need to have 2 here to get the 2 sodiums. We've then got 2 oxygens and we've got 2 hydrogens and we've got 2 chlorines. Okay, so that's the reaction for that one. If we're reacting it with hot and concentrated sodium hydroxide, so then it's still reacting with NaOH, but here we're going to make this NaClO3. Okay, that is going to be made in place of the NaClO. We're still going to make the NaCl. Okay, because we still need to have a disproportionation reaction. So the chlorine here, we saw this in a previous video, when chlorine reacts with water and it made HCl and HClO, we end up with chlorine in oxidation state -1 and chlorine oxidation state +1. Here the chlorine is going to be again in a positive oxidation state, so we need something where chlorine's in a negative oxidation state. So it still makes it NaCl, and we still end up making the water. So then again, this just needs to be balanced. This is a bit of an awkward one in terms of balancing. What you can see here then is we've got 4 oxygens here. So that would suggest that we need to put a 4 here to get 4 oxygens. I'm doing this lightly here because I'm going to come back and change this in a minute, but I want to show you the process. So I've got 4 oxygens. That then is going to give me 4 hydrogens. Okay, so then I would need to put a 2 there to get 4 hydrogens. But now I've changed the number of oxygens again, haven't I? I've now got 5 oxygens. So that would have to be a 5. So then I'd have to put, I need 1 extra hydrogen, so I'd have to have 2.5, and that's not going to work. So this actually needs to be a 3. Okay, so then I've got 6 hydrogens, so then this can be a 6. So now I've got 6 hydrogens and 6 hydrogens, 6 oxygens and 6 oxygens, so that's fine. And I've now got 6 sodiums as well. Well, I don't want to change this because that's going to mess up my oxygens again. I've just got the oxygen sorted. So if I've got 1 sodium there, then I'm going to have to put a 5 here to get the other 5. So I've got 6 sodiums, and now I've got 6 chlorines, so I must have 3 Cl2. So it is a bit of an awkward one to balance, that one. I would suggest that it's worth just learning that reaction. Okay. Then we've got this, it forms another chlorate, so sodium chlorate 7, used in the manufacture of matches. What is the formula of sodium chlorate 7? Right, so what this is telling, if it's sodium chlorate, then it's going to be sodium and chlorine and oxygen. And if it's sodium chlorate 7, that's telling us the oxidation number of chlorine is +7. We know that sodium is going to have a +1 oxidation number because it's a group 1 element. So that's +8. So then the oxygens have got to add up to -8. Well, we know that oxygen's oxidation number is -2, so we're going to have 4 of them to get it to add up to -8. So sodium chlorate 7 is going to have to be NaClO4. Finally, the last question here is state and explain the trend in the boiling points of the halogens. So first of all, let's state the trend. So the boiling point increases down the group. And the reason for that then, this is going back to knowledge of intermolecular forces. These are all diatomic molecules, aren't they? Cl2, Br2. So they are just going to be intermolecular forces. So this is because the intermolecular forces are stronger. But we can do better than that. We can say what type of intermolecular force it is. Okay, because these are just elements, Cl2, there's going to be no difference in electronegativity, so there's going to be no dipole. So it's just going to be London forces. Okay, so this is because the intermolecular forces, the London forces, are stronger down the group. So why? Why are the London forces going to be stronger? London forces depends on the number of electrons, doesn't it? Do you remember? London forces are caused by the uneven distribution of electrons, the fact that the electrons are always moving about, and then just for a fraction of a second, you end up with more electrons at one end of the molecule than the other. So you end up with this temporary dipole. Okay. So it's because the intermolecular forces are stronger down the group due to an increased number of electrons. And then we can say there's always an extra mark you can usually get for saying the stronger intermolecular forces will take more energy to break, or take more energy to overcome, let's say, leading to a higher boiling point. Okay, and there's usually an extra mark. You get 1 mark saying this is a stronger force, and then there's usually an extra mark saying, and therefore it takes more energy to overcome it. And that's true of any question about melting and boiling points. It's always worth putting that in to get an extra mark.